Hello and welcome to our lesson on estimating the least squares regression line. And if you look over here, least squares regression line is the real mathematical way of saying something you've probably seen already. A line of best fit is probably what you'll hear me refer or your teacher refer to it, or a regression line or a trend line. And what you need to notice is this red line that's there is not there until we put it there. So what we've done is we've got a scatter plot. We've got uh, test scores that rely on time spent studying. And there's a bunch of student reported time spent studying and then what they got on a test. So we're seeing there is a correlation. Time spent studying looks to be affecting the test scores. We would say it's a positive correlation because as you spend more time studying, the test scores increase, okay? Now this red line is going to be our LSRL or our line of fit right here. And what we're going to do is find slope and y-intercept and then use it to predict values. And probably the most challenging part is being able to explain the meaning. So slope intercept form for our LSRL, our line of fit, really looks quite familiar, except we did put this hat there. We call that a hat or caret. That means we're estimating, or sometimes you can think of it as an average, but it's our predicted y. So if you're asked what data was there, you use the information as the data came in, but then this we think is going to fit future situations, or we would use it to try to understand better what the connection is between time spent studying and test scores. Remember, test scores would be called our dependent, time spent is our independent variables. To be a little more specific, in this situation, if you do count this, like when we want to find a lattice point to find a slope, like if I went from this point here, 10, 65, up to this one, 20, 70, or even all the way out here. Usually we like to spread out our points when we're trying to predict our slopes. But wherever we went, we would realize it's got a rise of 5, run of 10, or a rise of, what do we got here? 65 to 95, rise of 30, run of 60. So the slope is 1/2. In context, we would say the same equation, the equation in context is the scores or test scores equals 1/2 time times the time plus 60. So we'll want to know how to interpret the meaning. In this case, the meaning is students are predicted to get at least a 60 on this test. Probably whatever studying they're doing for this test involves information they already know. They just have to remember it. Plus, it looks like there's some additional learning that needs to be applied. So your expected score or predicted score equals 1/2 times the time spent studying plus 60. So let's try an example here. Each example, sketch a line of best fit using a straight edge is a good idea, and then estimate the slope of my intercept, and then write the equation in context. So a pool is draining, so the volume of water depends on how much time it's been draining. So pool's draining. Context-wise, if I ask you whatever the slope is, we can see here the slope looks like it's negative 200, goes down 1400 for every 7 hours. So that's a negative 200. So we would say in context, this equation, this predicted equation, y hat equals negative 200x plus 1400, means you plug in a number for x. That's how many hours it's been draining at 200 gallons per hour. We can figure out what the volume that's left is. So the volume, predicted volume, minus 200 times hours plus 1400. All right, and technically I would argue that this doesn't even require the y-hat because I don't see the scatter plot. This is really just a linear relationship that we should be able to say y equals, but we're practicing here in context of taking data. Likewise, for this example, if we look here, species added to a list, we're assuming, I think we saw this somewhere, it's a species that are endangered. So the endangered species are going down. This is good news. We're not losing species of animals. Anyway, looking at the data here, we would take out a straight edge, put in a line of fit, calculate a slope, and predict a y-intercept. So this line was put in. We predict this to be a 110 for the y-intercept. The slope, we choose, you can choose any 2 points that you think fit best. We do like to spread them apart a little bit. So if I pick the point here and the point here, that's about as far apart as I can get. And I even predicted this 110. So 110 down to 0, that's a negative 110 rise over 0, actually 1995, up to 2002, let's see here, yeah, to 2001. This is 2002 out here. So 95 to 2001 is 6 years. It goes down, the endangered species reduced by 110 for every 6 years, or in a unit rate, 18.3 species per year are taken off the list. So y hat equals mx plus b, and that means the species equals negative 18.3 times the years since 95, plus the 110 that we started with for our initial value. Okay, movie circulation, movie movie rentals. This is going old school on you, back in the Blockbuster days. A movie would come out from the advertising and stuff. People are excited to see it, but every week that goes by, it becomes less interesting. Maybe new movies come out, other things happen, it loses its circulation or expected rents. So let's go through this in order here. We got a bunch of points. You want to put a straight edge down and be able to predict on these lattice points. I would say this point and this point looks like good ones. Predict what the slope is, predict what the y-intercept is, and then write the equation, and we'll also say it in context. So, line of fit, rise of negative 15, run of 20, negative 15 over 20 reduces to 0.75, or you could put 3/4 if you like fractions. So negative 0.75, what that means is for every week, 0.75 weeks that go by, the movies rented goes down by 1. Okay, so y hat equals negative 0.75x plus 32, which means the rentals equals a decrease of 0.75 per 1 week. I said that wrong earlier. It's a reduction of 0.75 per 1 week. That would be worth remembering. It might even be worth, whenever you see your decimals, maybe think of them as an over 1. And then the units was 0.75 rents per 1 week of it being out. All right, plus 32. So at the very beginning, they expect 32 rents per week, and then every week that goes by, they lose 3/4 of a rental, obviously. Plot the data and label the X and Y axes. Okay, this one, we're looking at pages being read and the time spent doing it. So pay close attention. We should do a pretty good job of telling you what the independent and dependent variables are. Usually the top row would be X and the bottom would be Y. So we need to make sure that you understand what depends on what. The pages that you read depends on how much time you spend reading. So as time spent reading goes up, the number of pages read will also go up. That's a positive correlation, unlike this, which was negative. And then we label pages read on the vertical and time spent reading on the horizontal. That's basically your clue. You see these units make sense for the time for the x-axis. Got your data points to plot. In this case here, we've already plotted them for you. Now you're looking at a data table. You plot the points, draw the line of fit, find a slope, predict a y-intercept, and write your equation. Plot the points, draw the line of fit, From that, we find our slope of rise of 9 from 1 up to 10. That's rise of 9. And a run of from 5 to 30. That's 25. So 9 over 25 reduces to, or is written in decimal form, 0.36. That means 0.36 pages read per 1 minute. Again, might be worth putting a divide by 1, or helps you understand the per, and you put the units on that. It really helps. So y hat equals 0.36 x minus 1. That means the pages that you read equals 0.36 times the number of minutes reading minus 1. Okay, that should give you what you need to get started on the homework. We'll see you in class.